start.
Okay, so I wanted to talk a little bit more about theorem 7.5.1, which states the following. If V and W are vector spaces over the reals, and T is a linear transformation, then we have this relation between the dimension of the domain, dimension of V, and the dimension of the kernel of the mapping, and the dimension of the range or the image of the mapping, right? This is the rank nullity theorem in the abstract case. So I gave two proofs in the notes. The first proof, I'll let you look at the notes. I'll try to say more about that later at some point or another. Basically what I do there is I use the coordinate mapping to change the given problem to a matrix theoretic problem. Basically the idea is, since these coordinate mappings are isomorphisms, you can discover things about linear independence and spanning in the abstract case by sort of ripping the problem back to the coordinates. And so once you're back down in the column vectors, then you can use matrix theoretic stuff that we already know. But I don't want to do it that way because I think this proof that I'm about to show you is more useful for linear algebra's sake. So
I'm going to zoom out for a little bit.
You're going to zoom out for a little bit? Okay, I'm going to erase that. Get it out of the way here once I...
Which part?
The
purple?
Proof of one and the purple part, yeah.
The proof of one.
Yeah. Okay, so can I erase it?
Yes, it's good.
All right, so I'm going to focus here on proof part 2. And so I'm referring to the numbering in the notes on page, let's see, my current version, roughly page 171, 172 is where we are. Okay, so let's get to it. So in order to prove this theorem, I use some of our basis in subspace theorems. First of all, I noticed the kernel of T is the subspace of the domain, and therefore I can choose a basis for it. Let's say fp plus 1 through through n. The numbering, I'm choosing a kind of weird numbering for it, if you can forgive me. The reason for choosing this numbering becomes apparent as we go on, but anyway, there's finitely many things in there, and I can just say I have p plus 1 to n. So I suppose p is defined to be what in my so basically, what's the counting here? P, trying to think of how to say P in terms of what's given. P is equal to n minus the dimension of the kernel. I think. Is that right? No, it's still wrong. I guess I don't know what it is yet. That's kind of the point. But how many things are in here? N minus p, right?
Mm-hmm. The dimension of the kernel p.
So I suppose if you ask me what is p, because that's the natural question at this point, is like, what is p? Well, I could define p to be what? P would be, just solve, right? P is equal to n minus, oh, it was what I said. It was n minus the dimension of the kernel. Okay, fine. Okay, so that's definitely something I could define without ambiguity, and I do that. And there you go. So to start with, the last p things here is the basis for the kernel. But I can take any basis for v and I can extend it, any basis for the kernel, and I can extend it to be a basis for the whole space, all right? So I take this basis and I extend it with this f1 through fp. Now f1 through fp are not in the kernel, all right? So f1 through fp are not in the kernel, which means that t of fj is not equal to 0 for j equals 1 to p. Okay, so by the way, excuse me, if any of those were 0, then that would mean that that f sub j was in the kernel, which would mean that there's another vector in the kernel which wasn't there already, which would be contradicting what we already have. So you know for sure that the images of these guys have to be non-zero if they're going to extend the basis for the kernel. Okay. So then the next step is to think about the range. The range of T is a subspace of W, right? So the range is a subspace of the codomain vector space. And that could be given a basis, the range itself can be given the basis T of F1, T of F2, all the way to T of Fp. Now how do I know that that's a basis? How do I know that these are linearly independent? Well, if you think about it, if there was linear dependence, then that would imply that that same linear combination of f's was in the kernel. You can manipulate it to get it's in the kernel, but we know that they're not in the kernel, so that's essentially why we can argue that they're linearly independent, so those are linearly independent. Okay, but then again we can use the basis extension theorem for the subspace. We can extend from this basis for the range to the rest of these guys, which fills out W. This is a basis for W altogether, right? And then you just count. Okay, so the dimension of the kernel plus the dimension of the range, what's that? It's equal to the number of things in the basis for the kernel, which is p, n minus p, rather, and the number of things in the image, which is p, is what I call p.
Mm-hmm.
And so the p's cancel, and you get n, which is the dimension of e, so the dimension of the kernel plus the dimension of the range gives me back the dimension of the domain. Of course, p you should recognize as being what? T is what we, I mean, in this proof, p is equal to the rank of t, right? In my notation at the moment. All right?
Mm-hmm.
And the nullity would be n minus p while I'm at it, all right? So of course when you add these, you get back n. All right, but we can be greedier. There's something else we can extract from this proof while we're at it. That brings us to theorem 7.5.2. So 7.5.2 says, are you over there?
Mm-hmm.
Same setup, V and W vector spaces, dimension of V being n, dimension of W being m, T a linear transformation, rank of the T is P. I'm assuming all of this, all right? Then there exist bases, beta and gamma for W, such that, beta for B, gamma for W, such that the matrix of T is the identity, the P by P identity matrix with zeros everywhere else. So the proof is very simple. You just let beta and gamma be as the bases we just constructed over there, all right? And if you just look at the matrix of that, well, that should be the T of beta gamma would be T of the first thing in the beta basis, the gamma coordinates of that, and so forth. Well, by definition, that's the first thing in the gamma basis, right? So that means it has coordinate vector E1, standard basis. Where is that? That's E1 is actually an element of Rm here, because gamma, phi gamma is a mapping from W to Rm, because gamma is, W is m dimensional, and so forth. That goes on until you get to the end of the part of the basis for beta, which maps to the image, right? Mm-hmm. The pth one, that gives you EP. And then these guys are T, fp plus 1 through n. These are in the kernel of T, so those map to 0, and the coordinate 0 is 0. And so you just look, what is that? Well, that's exactly the P by P identity matrix, because it's just like E1, E2, EP, and then zeros and the rest, and that proves the theorem. Now, if you go back, let's go back to the proof of the theorem, though. I've asked you guys to actually calculate. There's a problem like this in your homework, sort of, and there's, from a calculational perspective, there's a couple things here which are kind of like not immediately obvious how you would actually do them for an actual example, right? So if you think about this, it's clear enough we know how to find the basis for the null space. That's not hard. The kernel. But how do you extend the basis, right? That's always not entirely obvious. You have to pick something that's not in the span of these guys, right? And I don't know if I've ever really described a general calculational method for that. I just kind of do different things for different examples. I'm just saying what's in red here, when you actually got to a specific example, it's not entirely, there's some kind of guessing there for me for the most part. I haven't found it useful to develop a specific algorithm to solve that problem. I find it useful to guess in examples typically. And likewise here, it's easy enough to see what the part of the basis is for the range, but everything that's not in the range, how do you select these vectors for the basis? Well, that's kind of subtle. Let me show you how that actually goes for a specific example. The example I'm going to look at is not in the notes, and so I'm going to erase this because we're just going to. I probably shouldn't. Oh well. So here's the example. So I'm going to look at, so what I want to do is I want to actually find the basis beta and gamma like I just talked about in the theorem for this linear transformation. I'm going to look at T, going from R3 to P2, all right? And I'm going to define the, I'm going to try to look at it. I won't burden us with an example which is too horribly complicated, so I think this is a good example. T of x, y, z is equal to, let's do z minus x times t squared plus y minus z times t. All right, so here I'm looking at P2 as being a subspace of the polynomials in T over the reals, okay? So that's my definition. I mean, it's fairly clear that that's a linear transformation. I won't prove it. Just going to go on here. So I guess the first order of business is what's the kernel? What is it, something?
Oh, just stretching.
Just stretching? Okay. Kernel.
What?
Kernel of T is what? It's x, y, z, right? In R3 such that what? T of x, y, z equals to what?
0.
Equals to 0, right? So if I call that thing v, all right, so v is equal to what? V is equal to x, y, z with what? Such that z minus x times t squared plus y minus z times t is equal to 0. Now that's a polynomial equation, right?
Mm-hmm.
The only way I can have a quadratic polynomial equal to 0 is if each of the coefficients is separately 0.
Mm-hmm.
So I can read from the coefficients here, right? That, so from this guy I get z minus x is equal to 0. From this one I get y minus z is equal to 0, right?
Uh-huh.
I don't think I need any kind of highfalutin, matrix row reduction here to understand what's going on. I can just see that z is equal to x, right? And I can see that y is equal to z is equal to x, right? I can see that I can use x as a parameter here. And so basically, in view of that, my v is actually just x, x, x. Right? So I can easily factor out the x and see that everything in the kernel is a span of this guy.
Mm-hmm.
Okay, so following the theorem we just went through, I will define, so hence, define beta, and I'm going to leave 2 slots here. We'll fill in the blanks. Blank, comma, blank, comma, blank, comma, blank, 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 comma, and then the thing I know. So I put the kernel, the thing in the basis for the kernel last in the list in order to achieve, the identity pattern with zeros, where the identity is in the upper left-hand corner. That means I need to put the things in the kernel at the end of the basis for the domain. So I know that this is in the kernel, right? So this is that ambiguous thing I was saying. How do you extend a basis for a subspace, right? So what would you do, Sharon?
You can pick like other things that are
Right.
linearly dependent.
Pick other things that are linearly independent. There's also a very important principle here. Be lazy. So what is one lazy vector you could put here which would be linearly independent from that? I mean,
1, 0, 0.
yeah, 1, 0, 0. I like that. For the purposes of today, you're Asian, Sharon. I'm sorry, you're
I'm Asian by the
you're
white.
white or perhaps American Bailu. I don't know what's more politically incorrect.
Racist.
Yes, sorry. Okay, let me stop with my racism. All right. So how about
001.
I take your 001 and I trade you a 010, but yeah. I mean, you're right. 001 would also be a fine choice. The only reason I'm using 010 is because I've already worked that out. But it might be interesting to do the other. Okay, anyway, so that's a basis for beta, right? Now, how do I figure out what the basis is? How do I figure out what a basis is for the range? You see, one of the interesting things we're discovering in this proof is we can find a basis for the range by simply looking at the images of the things which are not in the kernel. provided that we're looking at a basis, right? And this is a basis. So notice that t of 1, 0, 0, t of 0, 1, 0, right? What are these equal to? You got to go back to the definition of the thing, right? So that means x is equal to 1, y and z are 0, so I get minus t squared. This is t of 0, 1, 0.
So y is 1.
Right, so I get t, right? And we already know that t of 1, 1, 1 is 0.
Mm-hmm.
Okay, great. So if I want those to correspond to like E1 or E2 and the basis for t, that means I should choose the basis for the range. I mean, for the codomain, you make minus t squared the first thing in the basis, right? And you make t the second thing in the basis, right? Right. If I let me just poor planning on my part. Let's try this again. Leave myself a little bit more room here. So let gamma equal to minus t squared t comma something we don't know yet. I just need something else which is linearly independent in P2 and completes the basis. I want to extend to a basis of the codomain, which is in this case is P2. What do I put there?
Not a 0.
Not exactly, not 0. 0 is not definitely not the thing to do. Here, while you guys are thinking about it, you might notice what's the let's see here. This was t of f1, right? This was t of f2. This was t of f3 in my proof notation.
Mm-hmm.
So the the coordinate vector of t of f1 with respect to the gamma basis was e1. The coordinate vector of t of f2 with a gamma basis was actually e2, because what the coordinate of t, if t is the second thing, that means its coordinate vector is e2, right? These force that. So what should I put here? You got lots of choices, right? But you can see what we're missing. We're missing things with constant terms, right? Like to build second order polynomials, you need constants. I've got no constants in here. I've only got the quadratic and the linear term, right? So I'm missing things like, P2 is what? It's the there's standard basis for P2. Well, a basis for P2, 1 t squared, right?
Mm-hmm.
So like, we're missing 1. So the thing I would think here without 1. Now you say, what's your algorithm for figuring that? I don't have an algorithm, I just guessed it, right? Kind of used common sense and looking at it, and that works for me on these kind of examples. Great, then you notice actually that kind of matters if there had been a t or a t squared dependence here. If I had put something with a t or a t squared dependence here, these wouldn't have worked out like that necessarily.
Mm-hmm.
But anyway, there you go. That's t of f3, of course, is however you slice gamma, that's 0, which is 0. And then, so the matrix of t with respect to beta gamma, 1, 0, 0, 0, 1, 0, 0, 0, 0, as advertised. So that's actually how to do it for this specific example. Now, in the notes, all right, I have do you guys have any questions about that? No. In the notes, I actually have a harder example. What?
Better for them to help them understand, you might want to put 1, like the purple one over there is in R, so they know it's just like randomly pick any numbers.
Pick which one? Pick purple?
Where you put the 1, we can pick, because that could have been 7, right?
Yeah, it's could be any number, because you put 1, they might be thought it's like it has to be 1.
Oh no, it could be, you could put anything there actually. That's the thing, is there's so many different choices. Like whatever I put here, I just
R.
have to have star, which is not an element of the span. of t and well, minus t squared and
Minus
nt.
t squared t.
But well, I don't. Maybe it's a little bit more than that, because I feel like if I had, like, if I put 1 plus t here, I mean 1 plus t is not in the span, right?
Mhm.
But I wouldn't want to put 1 plus t there. If I put 1 plus t there, right? Well, I guess it's still okay. Fine, it's still true that the coordinate vector of f1 is e1. I guess it's okay, but
Okay.
that worries me for some reason. But yeah, you could put a lot of other things besides 1 there. That was part of my point.
PM.
What time is it?
1.
Oh my goodness. All right, so let me finish this, let me wrap this up. I don't want to work through all this example.
And it's 21 minutes already.
Yeah, no, I just want to take a minute, because what's in the notes will actually help you solve the problem in the homework. Wish I could remember which number it was, but if you look at example 7.5.3 on page 174, I show how through specific row reductions you can take A equals to 1, 1, 1, 1, first column, second column, 3, 4, 0, 2, third column, 4, 5, 1, 3. Okay, so you can take this matrix, and I explain that if you take, I'll just show you the results. I mean, I explain how to calculate the matrices I'm about to write down in the example, but let me just go ahead and show you the end result of the example and discuss its meaning. Okay, so it's a 2 by 2, and I end up getting a matrix which is kind of big: 0, 0, 1, 0, 0, 0, minus 1 half, 1 half, 1, 0, 0, 1, 1 half, minus 3 halves. I'm not writing these in any particular order. Sorry. The matrix A is in the middle. And then over here I've got, and so I explain a method to calculate the matrices, which are getting you from A to, let's say, B. So we call this thing B. I'll call this thing P. This is A, and I've called this Q transpose in the notes. Oh, there's not a 2. I'm an idiot. I copied down the wrong matrix. So the last row in the Q I wrote was 1. It's supposed to be 1, 0, minus 1. Right. Okay, so what this shows you, guys, is this shows you that the matrix B and the matrix A, they're matrix congruent, because I found an invertible matrix and another invertible matrix, such that when you sandwich A between those, you get back to this. So this means that B and A are so-called, they're matrix congruent. Matrix congruent matrices have one thing in common. Well, I guess they have more things, but in particular, we know that the rank of A is equal to the rank of B. That's one big thing, right? And obviously, it's easy enough to read what the rank of A and B is from B. It's obvious that the rank is what? It's 2, right? But there's a little bit more here, guys. Like, I don't want to spend too much time blathering on for you guys, but you might notice that this actually has, this matrix, it actually has in it the basis beta as described in the theorem. This is, Q transpose is actually the basis matrix for the basis as described in the theorem. And so in particular, if you believe me, the last thing in if the nullity here of A is 1, the dimension of the kernel is 1, right? And if you believe me, then the method, this should actually be a basis for the null space of A. Now how do we check? Well, try multiplying. 1 plus 3 is 4, 4 minus 4 is 0, 1 plus 4 is 5, 5 minus 5 is 0, 1 minus 1, 0, 1 plus 2 is 3, 3 minus 3, 0. So you can easily see that the null space of A is actually equal to the span of 1, 1, minus 1. So one way to look at that example is I've given you a fairly complicated way of just calculating the basis for a null space without doing that thing we usually do. I actually show you, in some sense, a method to calculate the null space of a basis through doing successive row reductions without further like hand-to-hand combat with things, which is kind of interesting because every time we found the basis for a null space, we've had to like do a row reduction, but then write it down and then see how stuff. In fact, I mean, our calculation for the null space has always been by hand a little bit, not direct technology. But anyway, I'll let you guys look at. If you look at this, though, it will allow you to do that problem if you can't see it. Of course, you could try to model the proof of the theorem to solve that problem at the end of the homework. It really would be useful if I told you which problem it was, wasn't it?
Was it one in the email?
Curses. I need to find that homework. The time's a wasting. Do you have your homework in front of you?
Yeah.
Otherwise, I'm going to be accused of making people listen to this for 30 minutes. You know who you are.
26 already.
26, oh no. Oh my goodness.
Problem 96?
Time's a wasting. Yeah, problem 96 is the one I'm talking about. That's right. So, sorry, this 26-minute talk given to you just so you can understand problem 96, like the spirit of it. So, my apologies for the length of this blah blah blah. That's all. How do you turn this thing off, Bailey?
What?
How do you
Don't
make
hit
it
the red button.
stop?
Are you going to stop?
Yeah, stop.
Oh, just